Welcome to the continuation lecture of Part C revision, in which we are covering important problems on thin-walled sections, especially the comparison problems, and also a little bit important information on the derivation of thin-walled tubes, and also a few problems on the torsion of rectangular bars. So I hope you might have viewed the previous video in which we have covered the important portions of Sen-Venant's torsion theory and the solution of circle and elliptical cross-section using both Sen-Venant's approach and Prandtl's approach. We have tried our level best to bring you the important portions of Part C in this very limited time, but we are sorry that we were not able to cover all the portions. So what we thought is we would present at least some important topics so that this could be of some use for your final examination if you are able to go through at least. So I'd like to present from Part C this reciprocal theorem, Maxwell's reciprocal theorem, Castigliano's first and second theorem, the principle of virtual work, and minimum total potential energy theorem. So these four are basically theoretical derivations, very simple derivations only. If you are able to go through these four theorems, you will be able to score at least 5 to 10 marks minimum. Now moving further, we have application problems from the Castigliano's theorem also to find out the deflection. You can see some 2 or 3 problems from the previous university question paper which are already solved in the textbook. Now coming back to these first 4 theorems, they are frequently asked, in which the minimum total potential energy theorem is pretty simple. It will be asked for nearly 2 to 4 marks only maximum. Whereas reciprocal theorem and Castigliano's theorem, they are more frequently asked, and they can be asked for marks ranging from 5 to 10. Now sometimes Castigliano's theorem alone will be asked, in which you have to mention both first and second theorems. Now principle of virtual work is also asked for 10 marks once. So better you be familiar with all these 4, in which minimum total potential energy theorem is comparatively not lengthy. Now additionally, from Part C we have membrane analogy, that is Prandtl's membrane analogy, which was also asked for marks ranging from 4 to 6, in which you will be asked to explain the analogy. It is a simple comparison table in which you have to draw a column and you have to explain at least 4 or 5 points, which may fetch you minimum 2 to 3 marks, even though you are not able to explain the complete process. Now let us start with a problem from Part C. Now this problem is from thin-walled sections. Now given a thin-walled rectangular section, and we are asked to compare it with a solid section. Now the question is to find out the thickness T of this section for 2 conditions, same shear stress for same torque and for same stiffness. The dimensions of the box are given, and also the dimension of the solid circular section is given. Now let us analyze the problem. So problem on thin-walled section compared with a solid section. So the dimensions of the box is 2a by T. So 2a is the length, a is the breadth, and T is the thickness. And the circle is a solid circle of diameter A. Now case 1, both have same torque and same shear stress. Now what is the question? The question is to find out the thickness T. Now from the thin-walled sections theory, we have tau is equal to T divided by T into 2am. This we have obtained from T is equal to 2qa. Now what is this AM? AM means the area enclosed by the median line. If you are finding difficult with this term, you can simply say T is equal to 2qa. So Q is what is called the shear flow. Shear flow is defined by the product of shear stress and thickness. So I am replacing Q by tau T. So we have the basic equation T is equal to 2qa. Q is replaced by tau T. So I am defining what is shear flow. Shear flow is represented by the letter Q, which is the product of shear stress and thickness in a given section. So from this, tau is equal to T divided by small t into 2am. Now we have the circle, which is a solid section. Now the above formula doesn't apply for the solid section because it is not a thin-walled section. So for the circular solid section, we are applying T by J equal to tau by R. That means tau is equal to TR divided by J. Now our question is that for the same shear stress for both sections, so toe box is equal to toe circle. That means in this condition we are asked to find out what is the value of thickness, small letter t. So what is toe box? Toe box, let us substitute this formula, t divided by small letter t into 2 into AM. What is AM? Area enclosed by the median line. That is, median line means the line which is in the center of outer and inner lines. So 2A into A, that is length into breadth. The given dimensions must be with respect to the median lines. So AM is equal to 2A into A, which must be equal to toe of the circle, which is TR divided by J. Now what is J? J is polar moment of inertia, pi d raised to 4 by 32. So simplifying, we will get, now R we can substitute as d by 2. So if we simplify this, now before that, now the diameter d, in the question it is given as A, small letter A. So I am substituting pi A raised to 4 here. Now we will get T is equal to pi A divided by 64. This is the answer. Now second case, for the same stiffness. Now what does stiffness mean? Stiffness means torsional rigidity. So torsional rigidity is given by T by theta or Gj. So Gj of the box is same as Gj of the circle. Now let us assume, because since the data is not sufficient here, let us assume the G, modulus of rigidity, is same for both the sections. So if the modulus of rigidity is same, that means this J of the box is same as J of the circle. So J of the box, now box is a thin-walled section. Now J of the box, we have ready-made formula 4A square T divided by S. What is this A? Area enclosed by the median line, that you will learn from the derivation of thin-walled tubes. Now T is the thickness, and what is S? S is the perimeter or the total length enclosed by the median line. Now what is J of the solid circle? Now I have already explained the solid circle is not a thin-walled tube, so it is pi d raised to 4 by 32. Here diameter is given as A, so pi A raised to 4 by 32. Now let us simplify this. So J of the box is equal to J of the circle. So I am substituting AM for box as again 2A into A. Now what is the thickness? Thickness is given as T only, that we have to find out. Let us keep it as it is. Now what is S? S is the perimeter or the length enclosed by the median line. So for the box, it is 2A plus 2A plus A. That is, it will come to 6A. So now simplifying, we will get T is equal to 3 pi A cube divided by 32 into 4. Now let us discuss this question. Why closed sections are having better torsional rigidity than open sections? Briefly explain. It was asked for 4 marks. Now let us see what is an open section and what is a closed section. Now this is a completely closed section, and now this is an open section. Now what is the difference? The difference is that in a closed section we can establish at least one shear flow circuit. The arrows are representing the shear flow. As I have discussed in my last lecture, what do you mean by shear flow? Shear flow is the product of shear stress and thickness, and it is represented by Q. Q is equal to tau T. So we can establish one complete circuit, that means it is a closed section. Now here the circuit is incomplete, so this is an open section. So the closed section, this closed section resists much more higher torque than in the open section, and also the deformations after the application of torque is very much less in closed sections than in open sections. So due to these two reasons, the torsional rigidity of the closed sections are better than that of the open sections. Now we have an important derivation on how to derive the expression for angle of twist, strain energy, and capital J for a thin-walled section. Now this derivation is frequently asked. I hope you can learn by yourself. Due to shortage of time, I am not explaining, but I will tell you what are all the important equations to learn. So a thin-walled section derivation, initially you have to draw the figure, and then you have to explain what is shear flow. So shear flow, as I have discussed earlier, it is the product of shear stress and thickness at a given section. The shear flow will be constant throughout the tube. That is, the product of tau and T will be constant throughout the section. Now after explaining what is shear flow, you have to draw the cross section of the thin-walled tube as shown in the figure with the median line represented, and you have to show the AM area that is mean area, and you have to mark the parameters, and afterwards you have to derive what is the expression for capital T. So capital T is equal to 2QA or 2QAM to be very specific. So AM is called the area enclosed by the median line. You can see the area enclosed by the median line. So from this you can substitute for Q, that is the shear flow, as T into tau, that is the product of thickness and shear stress. So from that you will get tau is equal to T divided by 2 into AM. This equation is very important and is frequently used while solving the problems. Now after that we have to move to the strain energy of the shaft. So U we can derive as T square L by 8GAM square into closed integral of ds divided by T. Now from the Castigliano's theorem we can have the expression for theta as T divided by 4GAM square into closed integral ds by T. Now further we will get the final expression for theta is equal to Ts divided by 4GAM square into T. So this expression you need to by heart. Now moving further we will get the expression for J as 4AM square T divided by S. So what is S? S is the length of the median line. So this equation for J, equation for theta, equation for T and equation for tau, these four equations you have to be very familiar while solving the problems of thin walled tubes. Now let us see a specific case. We have two specific cases only, that is one for circular tube. Here you can see a circular tube of radius, that is the radius to the median line as R, and T is the thickness. Now you can see what is the area enclosed by the median line, that is pi r square. So R being the radius till the median line. So shear stress we have obtained from T is equal to 2QAM. So Q is substituted as T into tau. So from this the shear stress expression is obtained. Now what is the length of the median line? Length of the median line is this total perimeter which is given by 2 pi r. Now what is the torsion constant? Torsion constant we have substituted from J is equal to 4AM square T divided by S, we will get as 2 pi r cube T. So these equations might be required for solving the problems. Now let us discuss a similar problem from the thin walled sections, where given a cross section of square type shaft subjected to twisting moment and also given maximum shear stress limit as 250 giganewton per mm square. You are asked to find out the torque and angle of twist if the shaft is 1.6 meters long. Now this is a solved problem in the textbook. Now here you have to take care that all the units are given in Newton per mm square and the sides are also given in mm. So you need not complicate by converting into SI units if you are very much familiar with doing this kind of mathematical problems. So here we have the shear stress formula, tau is equal to T divided by 2AM. Now what is AM? AM is the area enclosed by the median line. Area enclosed by the median line, you can see this length is 50 and this length is 55. So this dimension is the average of these two values, that is 52.5. So AM is maintained as 52.5 square, that is a cross sectional area. Okay. Now what is the thickness? That is 55 minus 50 will give the difference between these two dimensions, and you have to take the half of that dimension to get the thickness 2.5. Now what is T? Now from this equation you can find out T is this much, you will get the answer. Now what is the length of median line? Median line, now I have told this dimension is 52.5. So the perimeter is 52.5 into 4, that is the length of the median line. Now angle of twist, as I have told you earlier, to remember the formula, you might be saying that is Ts divided by 4GAM square T. You might not see this letter L in the earlier formula. Why? Because the earlier formula is for angle of twist per unit length. Now here it is given that the length of the shaft is 1.6 meters. So in order to account this, you have to multiply it with capital L, and it is maintained in mm, that is it is multiplied by 1000 because all the units are in mm. So you have to substitute accordingly to get the final answer, and the answer will be in radians. Now one more problem from the thin walled sections, where you are asked to compare both the thin walled sections. Now this one is a circular thin walled section and this one is a square section. Now what is the question? The question is to find out the ratio of shear stress, the shear stress of this section to this section. Now given thickness and circumference of two sections are equal. Now you have to find out the ratio of shear stress for two cases. First one, equal twisting moment applied, and second one, equal angle of twist. So here both are thin walled sections only. So now given TC is equal to TS, that is thickness of the circular section is equal to thickness of the square section, and the circumference are equal. So what is the circumference of circle? It is 2 pi r. Now the radius is given as a, so I have written 2 pi a, which is equal to circumference of the square. What is that? 4 times the side of square is b, so 4b. Now equating, I will get a relation between b and a. Now what is the question? Question is to find out the ratio of shear stress for two cases. So first one, equal twisting moment applied. So twisting moment is basically torque. So we have the equation for torque of thin walled sections. T is equal to 2qa, or 2qam to be precise. So what is q? Q is the shear flow, which is replaced by tau into t. So T is equal to 2 tau t am. What is tau? Shear stress. T is the thickness. What is am? Area enclosed by the median line. So here we have torque of the circle is equal to torque of the square, which means I am introducing the suffix of circle as C to all the components in the LHS and the suffix S to all the components in the RHS. So then I will get 2 tau C TC into area enclosed by the circle is pi a square, that is the cross sectional area. Remember, this is not the surface area, this is the cross sectional area, which is equal to 2 tau s ts into b square. B square is the area enclosed by the median line on the square. So what is the question? Question is to find out tau c by tau s. It will come to this equation. Now here you have to substitute either for b or a as obtained here. Then only you will get the final answer, pi by 4. Now let us go to the part 2 of the question. Equal angle of twist applied. That is theta of c is equal to theta of s. Theta of circle is equal to theta of square. So which means we have the equation of theta for thin walled sections as Ts divided by 4gam square t. So T is the torque, S is the length enclosed by the median line or the total length of the median line. What is G? Modulus of rigidity. Am is the area enclosed by the median line and T is the thickness. Now remember, now the case is changed. Only given theta c is equal to theta s. They have not told Tc is equal to Ts. So we cannot just write Tc is equal to Ts. So here we have the equation for T is equal to 2qam. So Q is again substituted as 2 into tau into T into am. So now let us expand the equation, that is theta c is equal to theta s. So now 2 into, I have substituted for T as 2 into tau c into Tc into amc into sc, that is the perimeter of the circle, divided by 4g amc square Tc, which is equal to the corresponding components of square. Now what do I need? I need the ratio of Tc and tau c and tau s. So tau c by tau s is the area I need. I can cancel the corresponding components and it will come to 4b by 2 pi a into pi a square by b square. You can work out in detail, and I am getting 2a by b. Again I am substituting for either a or b from the relation I have here, which will come to 4 by pi. Now here is a different problem, which is from the multiply connected cells, and you are asked to find out the angle of twist per unit length when the two tubular sections are connected as shown, and given a torque of 30,000 Newton meter is applied, and also the value of G is given. So let us divide this section into two cells, 1 and 2. So given T is equal to 30,000 Newton meter and G is equal to this value. Now we have to find out, now this is a standard procedure, let us not make it complicated. Now we have to find out the closed integral of ds by t for each cells. Now what does that mean? Now I have told already we are dividing it into two sections, cell 1 and cell 2. So closed integral ds by t means, now for this cell 1, I am calculating the s by t value of all the dimensions around this cell. So what does that mean? So closed integral ds by t is this length divided by this thickness plus this length divided by this thickness plus this length divided by this thickness plus this length divided by this thickness. So what do I obtain then? Closed integral ds by t for cell 1 is equal to 30 divided by, now what is this thickness? This thickness is 0.75, which is given here. So 30 by 0.75 plus, now this dimension, it is again 30 given, 30 by 1.5 plus this dimension is again 30 divided by 1 plus this dimension is again 30 divided by 1. So I will get the value 120, which is I represent as small letter a1. Closed integral ds by t for cell 1 I am representing as a1. Now similarly for cell 2 I am calculating ds by t, which is equal to this dimension by this thickness plus this dimension by this thickness plus this dimension by this thickness plus this dimension by this thickness, which I am getting as 160, which I am representing as a2. Now I am naming this portion as web. This common portion, which is the neighborhood of cell 1 and cell 2, I am naming it as web. Now I am calculating the closed integral value of ds by t for the web, which is equal to s by t, because it is only having this channel. So this dimension divided by this thickness, which is 30 divided by 1, which is equal to 30. And I am naming it as a12. Why I am naming it as a12? Because it is sharing cell 1 and cell 2. It is a channel sharing cell 1 and cell 2. So I am naming it as a12. Now I have the ready-made formula for 2g theta. For cell 1, 2g theta is equal to 1 by a1 into a1 q1 minus a1 2 q2. So this formula you need to by heart. So 2g theta is equal to 1 by a1. Now what is capital A1? Capital A1 is the area of the cell 1. Now this is a square section. The area is 30 square, which is 900. Now a1 q1. A1 is closed integral ds by t for cell 1. Now what is q1? Q1 is the shear flow for cell 1, that I will explain very soon while proceeding to the problem, minus a12 q2. Now why I am subtracting a12 q2? Because I have told this web is sharing cell 1 and cell 2 channels. Now in order to subtract the effect of cell 2, I am subtracting a12 q2 from this value. Now cell 1 represents 2g theta is equal to 1 by 30 square into 120 q1 minus 30 q2. Now similarly I am obtaining cell 2, 2g theta is equal to 1 by a2 into a2 q2 minus a12 q1. Now what does this mean? This means I am subtracting the effect of cell 1 from the channel to get the correct value for cell 2. Now this 2g theta is same for both equations. So I can equate equation 1 and 2. Now if I equate equation 1 and 2, I will get a relation connecting q1 and q2. Either I can write q1 in terms of q2 or vice versa. Now what is the total torque? The total torque, this equation you have to by heart. T is equal to 2q1 a1 plus 2q2 a2. So a1 you know. Now a2, I think I didn't mention what is a2. a2 is same as, because it is a square section, the area is one side dimension square, that is 30 square, that is capital A2. So 2q1 a1, here q2 you can substitute in terms of q1. So you will get an equation connecting capital T and q1. So from that you can write what is q1 and what is q2. Now you can go and back substitute in any one of these equations. 2g theta is equal to 1 by a square, the corresponding area, whether it is for cell 1 or cell 2, into, you can substitute the corresponding elements to get the value for theta. Now one thing you have to concentrate is that now all the values are given, the dimensions are given in centimeters, while the torque value and the g value is given in meters. So you have better, you can proceed the problem in centimeters, and finally you can substitute, while substituting t you can just convert it to centimeter, or otherwise if you are converting every dimension to SI unit, the problem will be a bit difficult. So whatever convenient for you, you can proceed accordingly. Just be careful with the dimensions while solving the problem and find theta accordingly. So let us discuss a new topic, that is torsion of rectangular bars. So previously once or twice this problem of rectangular bars had been asked. So let us discuss. This is very simple. So here a section of square shaft is given 5 by 5 centimeter and a torque of 5000 kilogram centimeter is applied. You have to find out the toe max and angle of twist per unit length. Now here we have three things. The first thing is you need to know what is the B by H ratio, that is breadth to height ratio. So from this we can understand that the breadth to height ratio is 5 by 5, which is 1. Now, we have two equations. These two equations you need to by heart. Tau max is equal to capital T divided by alpha BH square. And angle of twist per unit length is theta is equal to capital T divided by beta into capital G into BH cube. Now, this alpha and beta are constants. Now, actually these values should be supplied for the examination, but I haven't seen them supplied. So, what you can do is you can assume a random value of 0.2, because these alpha and beta values are obtained depending upon the B by H ratio. So, you can write down the B by H ratio, and you can write down, since the values are not given, we can assume alpha equal to 0.2 and beta equal to 0.2. So, now tau max is equal to capital T divided by alpha BH square. You can substitute for alpha 0.2. B and H values are already given. Now, only thing you have to remember, you have to take care with the units. Now, here 5000 kilogram centimeter, that should be converted to Newton meter or Newton mm, whichever is convenient for you, and you have to work out with the units accordingly. Now, also here capital G is not given, that is modulus of rigidity is not given. So, you have to assume that a suitable material, or you can assume G is equal to 80 gigapascal or 100 gigapascal according to your wish, depending upon the material selected. So, now after substituting, we will get the value for tau max and theta in radians. Now, let us discuss one more problem. This was asked for 10 marks for the previous university examination. Now, a road with a rectangular cross section. Now, one thing you have to take care is that you have to differentiate the problem of thin walled tubes from a rectangular shaft. You have to carefully read the question, and you have to see whether thin walled tube is there. If thin walled tube is there, the section is entirely different and the formulas are different. So, here it is mentioned a road with a rectangular cross section used to transmit torque. Now, this has two sections, two separate sections, one of a particular length and another of different length, and the width is the same and G is also given. Now, here in section 1, a torque of T1 of 750 Newton meter is applied, and here another torque of 400 Newton meter is applied. You are asked to find out the maximum shear stress in the rod and also the angle of twist. So, for solving the problem, we will get a value for tau shear stress for this section and another value for shear stress in this section, and you have to see which value of tau is higher. And for getting the angle of twist, we will get an angle of twist for this section and a different angle of twist for this section, and you have to add both angle of twist to get the total angle of twist per unit length for the section. So, now as I have told earlier, what is the B by H ratio? So, B by H, now let us analyze portion 1. So, B by H ratio is 60 by 40. So, it is 1.5. Now, you can assume, since the values are not given, let us take alpha equal to 0.2 and beta equal to 0.2. Now, what is the torque acting on this portion? The torque acting on this portion is this torque plus this torque is applied here. Even though it is applied here, this torque will be effect here also. So, the net torque acting on this portion, on the left portion, is T1 plus T2, which is this value. You please take care of the units while solving the problem. Now, what is the shear stress acting? So, we have the formula for shear stress, T by alpha BH square. You can substitute the corresponding B and H to get the tau max for this portion. Now, let us analyze the second portion. The torque T is equal to 400 into 10 raised to 3 Newton mm only. You remember, the torque is applied on the rightmost end, so that torque only will affect on the rightmost side. Earlier on the section 1, the effect of T1 plus T2 was taken into account. Now, what is the, now here also you have to find out the B by H ratio. Since the values are not given, you can assume alpha equal to 0.2, beta equal to 0.2, and you can substitute the value for tau max is equal to T by alpha BH square. Substitute the corresponding values for B and H. Now, angle of twist, we have the formula T divided by beta G BH cube. Now, why a L is multiplied here? Because we have the formula for angle of twist per unit length. Now, here the length of the shaft is given. The length of the left portion and length of the right portion also is given. So, you have to multiply it with a capital L. So, you have to find out the theta of the left and theta of the right, which you will get in radians, and the total theta is theta left plus theta right.